go. Well, I'll put us in the gallery view. Display us. Everyone should be able to see us now. So have you done more books before this? Was this your first?
No, this is the third
Third, okay.
With Brian. Yeah,
Yeah.
so the third popular science book. Yeah, we've written one on relativity called Why Does E equal MC squared, and then we wrote one on quantum physics called The Quantum Universe.
I I always find there's sort of like a boundary. There's people who like write that one book and then they're like, I'm never writing another book again. And then the people who can't seem to get enough of it.
Yeah, I have mixed feelings about it. So I kind of when I'm finished writing a book, I kind of never want to see the book again
Yeah.
after I've finished it.
Yeah, totally.
But I feel that I just feel that I want to write these things down, and I quite enjoy the process of getting my head together to write what I write.
Well,
So the process so I write partly for selfish reasons, really. I mean,
yeah.
it helps me to think about why I do what I do.
Well, it's funny. It's almost like as you explain stuff, like you're about to explain a bunch of stuff today on with using your various. People are talking my sound's a little low. Using your various ways of explaining things. I'll turn that up a little bit. And then after a while, you've sort of said the same thing enough times that it's time to put that all now in a book. Like you've I find like what I tend to do, and they turn into articles or videos for me, but I go through this process of explaining the same thing again and again and again to people, and I fine tune, like I can sort of see and go like, oh, that didn't quite resonate, they didn't quite get in their head. Okay, let me try again. And then after a while, you get these, this collection of ways of explaining some of the newer stuff that are clearly getting through to the people that you're talking to, and then you're like, okay, that's now a thing to turn into to release it to the wild. So it's that back and forth. And if you don't take that time to kind of harvest the ideas and explainers and the education that you've created, then it feels like it's sort of lost into the nothingness.
Yeah, I know what you mean. I mean, the stuff that I've written about is the stuff that I've been teaching
Yeah,
for
yeah,
years.
totally.
For example, yeah.
Okay,
Yeah.
cool. Well, I'm gonna say hi to a bunch of people, and then we're gonna start the show. That wasn't even the show. All right, hold on. Hello to Adam Synergy, Andy Fusion, Arnold Post, Barrett Kleinkar, Colin Jones, David Dunn, DKKN, Eric Knapp, Fleming Thurnberg, Galaxia, Gareth Blake, Graham Walbridge, Granville White, Harry Patrick, Henrik Bo Anderson, Hugo Burnham, James Haney, John Gallant, John Suffel, Johnny Zed. Jolene is watching. Jolene Creighton. Unless you're on Jolene's computer. Anyway, Malcolm Bond, Michael Jobin, Mr. The Grievous, Nancy Graziano, Patrick Sullivan, Paul Gracie, Peter Quinn, Raza Siddiqui, Brian Howell, Seth Cooper, Stavros, Pachadukas, Stephen Hawkins, Umu, and Zappan Zappa. And hey, everybody, welcome to the Weekly Space Hangout. All right, let's get this started because we don't have a lot of time. Jeffrey's got a book and has written a book, but must leave. So let's get it started. There, back to me, back to this. All right, let's go. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, June 9th, 2017. I'm Fraser Cain, publisher of Universe Today. This week, we've got a sort of a shorter show. Not a lot of the team is here today. In fact, just one of the team is here. So we're good. Just a couple of stories. We'll see what happens with today's show. We're going to be talking about Alma's discovery of the secret ingredients of life found around distant stars and a possible explanation for the WOW signal. Joining me this week is our one new rookie contributor, Sari Marquardt. Welcome to the show.
Thanks so much, Fraser.
All right. Marquardt. I will get it.
This.
All right.
It's beautiful.
All right. There you are. All right. Awesome. So, and our special guest, Dr. Jeff Forshaw, doesn't have a lot of time, so we will get right into the interview. So, Sarah, we'll see you in about 20 minutes. All right. So, as I said, our special guest this week is Dr. Jeff Forshaw, who worked with a certain guy named Brian Cox to produce a book called Universal Guide to the Cosmos. Jeffrey, welcome to the show.
Nice to be here.
All right, so for people who are not familiar with your work, why don't you let people know who you are and what you do?
Well, I'm a professor of particle physics at Manchester University in the UK. And this book that you just held up, Universal, it's a book that is ostensibly about cosmology and about what we understand about the physics of the Big Bang and potentially what created it. But the kind of subtext to the whole book is how we figure anything out. How do scientists go about securing knowledge about the world in which they live? So the book kind of starts out with some really simple observations of the world, like the radius of the Earth, the mass of the Earth, how old the Earth is, how old the Atlantic Ocean is, how far away Neptune is. And we kind of, the fun part of writing the book was that we actually can do a lot of those measurements just doing kind of, I mean, it's the kind of stuff that you can do at home. So the distance to Neptune, even the measuring the expansion rate of the universe is something that you can kind of mess around with. If you've got some pictures of spiral galaxies, you can actually work out the expansion rate of the universe yourself. So it's a very hands-on approach to securing scientific knowledge. And yeah.
Well, that's a really tough line to do, especially when you're creating a book that's going to be out for the public. I mean, the way that you as particle physicists and cosmologists talk is you talk in math. And when you're trying to show somebody the simple way to understand that this underlying process is happening is you're like, see, when we take the derivative and we take the gradient of this equation, the linear algebra works out so that it's obvious. And the other mathematician agrees with you and you go about your day. But when you're trying to take that stuff and communicate it to the layperson and math is poison when you put that in your book, how do you work around that?
Well, I think this idea, I mean, it's true. It's true that to really quantify and put a number on things, which is kind of characteristic of a lot of science, you want to actually put a number on something, then you need a little bit of maths. But it's not the case that the maths in almost all pieces of physics, you can explain it using really quite simple mathematics. So, I mean, one of the things that we do in the book is actually work out the radius of the Earth from an observation made by a colleague of ours who went to visit his father by the seaside in South Wales. And he noticed that perched on the horizon was a navigation buoy, just kind of bobbing on the horizon. And from knowing the distance to that buoy bobbing on the horizon, it just happened to be coincident with the horizon. In fact, he came into my office and said, Jeff, I've got a good thing for your book, right? There's a buoy that just happens to be coincident in the horizon when you stand on the beach near where my father lives. And the maths involved to work out the radius of the Earth based upon the observation that this buoy is bobbing on the horizon it's a little bit of high school trigonometry. Now, I mean, in the book, we do it. We do that little bit of high school trigonometry. It's kind of in a little boxed section. But what's needed is to know that there is a process, really. So you don't even need to know, you don't have to follow the maths to be able to get the point.
Now you talk about some of, going back to the earliest stages of the universe, the part that really we're all so fascinated by. And we have this wonderful tool. We have the cosmic microwave background radiation, this all-pervasive afterglow from the Big Bang, but it is a limit. We only can see up to about 380,000 years after the Big Bang. But there was time before that cosmic microwave background. How do you go further?
Well, we can take a photograph of the universe. That's what the cosmic microwave background is. It is literally a photograph of the universe when it was 380,000 years old, which of course is almost just after it was born, because the universe is 14 billion years old. So it's very early on in the history of the universe. And the picture that we see is the picture of a very hot gas, essentially, at that time. So the universe, and we have this precious photograph of this radiation, but it's got patterns in it. It's kind of got some regions are a little hotter than other regions. So we can see this picture of the early universe where we've got this gas which is variously hot and cold in different regions. That pattern presumably came from somewhere. Something caused that pattern. So in that sense, if we have an idea of what caused it, which presumably happened at some earlier time, then we can get information on the earlier time because we can see the photograph. Right, so it's a little bit like, say, you see a photograph of your friend then or a family photograph. Then you can infer quite a lot about what happened before the photograph just by looking at the photograph. So it's true that we don't have direct observations, not yet anyway, on what happened earlier than that in the universe's history. But just having that photograph itself is a gold mine of information. In the future, with gravitational waves having now been seen, so these potentially offer us the possibility to see even further back and closer to the Big Bang. But that's just that field of astronomy is just starting out, where we can kind of hope to be able to observe gravitational waves from the time of the Big Bang. So there is hope in the future that we could do even better.
Yeah, I mean, the CMB is like the most useful tool, one of the most useful tools in astronomy. It just keeps giving and giving. And like each time there's like new theories and ideas, turns out that data was in the CMB all along.
Well, for me, and one of so I was there's a theory called inflation, which in essence predicts the Big Bang. So it's a theory that says the Big Bang occurred as a consequence or at the end of a process where the universe was actually expanding really rapidly. So just before the Big Bang, the universe was a very cold place, very cold, empty place. And almost like dew forming in the morning, it kind of filled up with these cold particles. So it was essentially the universe was filled with a cold gas of particles, which then underwent a kind of radioactive decay to produce the hot, dense particles of the Big Bang. That theory of inflation, it always seemed too far-fetched to me. I mean, I'm a particle physicist, not a cosmologist originally, but I got asked to teach a course on inflationary cosmology to our fourth years in Manchester, and so as a consequence, I worked through all these calculations, and I became convinced that this has got something. It's so ridiculous because it is a theory that's predicting. In principle, it's predicting the origins of the Big Bang. It's saying where the Big Bang came from. And the wonderful thing about this theory is that it predicts this photograph, the cosmic microwave background. The particular pattern that we see is predicted as a result of quantum physics when the observable universe was far, far smaller than the size of a single atom. So it's utterly mind-blowing in its scope, this theory. Clearly the most audacious idea in science, has to be. And
and we were almost there, right? I mean, 2 years ago, if we would have had this conversation, we would be so excited about the discovery of primordial gravitational waves in the CMB to show us this sort of afterglow of inflation. And then now with the Planck data, that's been thrown into a little bit of a question. But now, but as science goes, there's now 4 or 5 different separate attempts to map out the polarization at different frequencies to try and get to, take another crack at it and get to the answer. I mean, is there anything else that will tell us so much about the universe than being able to make that kind of an observation, to push back right to those first moments and understand how we got to what we have today?
Well, this is actually a slightly worrying aspect of which both particle physics and cosmology find themselves in now. in that they're both theories about, on the one hand, the fundamental nature of the material substance that composes the universe, and on the other hand, the origins, the structure of the universe on its largest scales. They've been so successful in the last 20 years with the completion of what's called the standard model of particle physics at the Large Hadron Collider, and with these wonderful observations that have been made by these satellites that have measured, in particular, the cosmic microwave background, but also wonderful measurements of large galaxy surveys, just mapping out the trillion or so galaxies which are known to exist across the cosmos. Those maps, they're so constraining, and in both cases, in both particle physics and in cosmology, we actually have a really successful description, which by themselves they don't indicate where the next development will be. So there's no guarantee that we're going to be able to find, do some observation in the universe. The measurement of the polarization of the microwaves that constitute the microwave background, that could potentially have a very important information, which would allow people to learn more about what happened during inflation and provide stronger evidence that it really took place. But apart from that, I think cosmologists are nervous, that it's, so the idea, I think, but that people have felt like this many times before in the history of science. There's a famous quote, I forget, somebody like Lord Kelvin or somebody like that, at the end of the 19th century, essentially saying that all physics was mapped out.
Yeah.
And the way forward really came by people just observing and measuring things. So it may be that the theorists, we're not smart enough to, we've got our ideas, but we don't know where to look. And it may be that by making ever increasing, ever more sophisticated observations of the universe, that we get an indication of where the new physics goes.
Yeah.
Right? So I wouldn't be. It could be that the whole thing gets turned on its head by some completely unexpected observation. That's probably has happened more often than not in the history of science.
Yeah, and I think that the thing that I find really exciting, I try to keep reminding people that they're watching this stuff get figured out in real time. You're watching the scientists and the observationalists and the theorists struggle with all of the different ideas and all the observations that have been made and all the competing theories and all of the math, and they are working forward step by step to try and puzzle this out. And then you compare that to all this other stuff that's essentially mostly settled science, that in some cases you can appreciate all the stuff that's been figured out, like the size of the Earth, and then other stuff you're watching this get uncovered in real time, and it is the process, and enjoy the discovery as it comes out.
The scientists themselves, right? There's a great quote from a friend of mine who says he loves it when he's confused, because it means he's on the cusp of learning something new.
Yeah, that's funny.
And so that state of not knowing things and being in pursuit of trying to understand and secure knowledge, reliable knowledge, that's the part of the excitement. You can't be impatient.
Yeah.
You kind of, you can be impatient. You want to figure it out, but that nature is the way nature is, and if you can't, there's no shortcut. You just got to enjoy the process, and
Now I know you've got to run, but I just want to now let's plug the book. I'll hold up my copy here. Can you hold up your copy in front of you?
I can, yeah.
So we've got sort of a stereo version of the book here. So this is Universal with really your name should have gone first, I think. But Dr. Jeff Forshaw and
I think you're entirely right.
And this other guy
should have done. Yeah, there we go. Yeah.
He does something anyway. Thanks so much. Now, how can people find out more apart from, of course, purchasing this and the previous books to understand in great detail how we know all this stuff?
Probably a good starting point.
Yeah, it really would.
My Twitter handle, which is at JRF1968.
JRF1968.
JRF 1968.
Perfect. All right. Well, it was great having you join us. Good luck with the book. Say hi to your co-author, and
I will do. Yeah.
and good luck with everything. And hopefully we'll get to the bottom of this, and you can write one more book that says it's all been figured out.
Of course. Yeah.
It was great to hang out with you. Thanks a lot.
Thanks, Fraser. Cheers.
All right, cool. Well, that was a lot of fun. Man, now when I dig into the book, Sarah.
Yes.
It's just the twain of us today, but
I
we've got
know,
a couple
right?
of stories, and one I think is going to keep us busy for a while, and I think people are going to be pretty excited about. So we can talk about that.
Wonderful.
Oh, great! Someone just ordered the book.
Oh,
Awesome.
sweet.
Yeah.
You have to read it now.
Yeah.
I have to read it.
So a couple of people were mentioning in the comments that I actually just covered this topic, so it's all sort of fresh in my brain. So I actually just did 2 episodes. One last week was how does inflation, like what is inflation, cosmic inflation, what's
Right.
our understanding of that, and then the other one that we just did was how do we know the universe is flat. And so those sort of 2 topics sort of cover a lot of stuff that we talked about today. So if people are interested, if you haven't already, subscribe to the channel, go back through the Guide to Space episodes. They were just the last couple, and there's some more interesting ones coming up as well. All right, so let's see. I choose. So let's talk about ALMA. Let's talk about the discovery of the building blocks of life around other stars.
Fantastic. So this just came out yesterday. It was unembargoed. So ALMA in Chile detected traces of chemicals that make up the basic ingredients needed for life. So huge deal. Everyone's really excited about this in the scientific community. They were found about 400 light years away in a multiple star system. And the stars in the system essentially go on to evolve just like our sun. So that's why it's of particular interest to us. So the particular molecule that was found, it's methyl isocyanate. I don't know if I'm pronouncing that totally right, but it's been discovered for the first time in these protostars, the huge clumps of gas that these stars form from. And in it is carbon, hydrogen, nitrogen, and oxygen atoms. So this particular system was actually already studied by ALMA back in 2012. And they also found another ingredient necessary for life. It's a simple sugar. So everyone's extremely excited about this. It goes back to the big debate that scientists have been having for a while about how life originated in our solar system in particular. A lot of people believe that it either originated completely on the surface of the Earth, or some building blocks were formed in the solar nebula prior to the formation of the Earth and then delivered there by comets to our planet. So this particular discovery really points toward that latter theory. It also suggests that planets around other stars similar to the sun could also take that kind of similar route to harbor life. So this is just really exciting in a lot of ways.
Yeah, I mean, I think of course, one of the greatest unsolved questions in science is where did life come from? This idea of abiogenesis, and
Absolutely.
How do we get from the raw material, the carbon, the nitrogen, the oxygen, etc., to some kind of self-replicating molecule, and those building blocks of life, the amino acids, the peptides, and things like that. How quickly can you get them forming that can then move into, into the more complicated life forms? And so to know that these things are just like out there in nebulae, just floating around, ready to turn into extraterrestrials is pretty exciting.
Exactly. And if it happened once, we're just, it's pretty evident that it would happen again. So it's super exciting. It's just a matter of when, or if it already has happened somewhere that we haven't seen yet. And then what's next for the complex molecules that we're going to discover? I mean, we're bound to keep finding more things that would be evidence of life being able to be created elsewhere.
Let's see. So Arjun is asking, would methyl isocyanate be a chemical that was abundant in the early Earth? Would have been involved in single cell biology?
So I don't know if I can answer that very well.
Yeah.
I'm not super versed on biology, but my understanding is that these are the elements that are needed to begin life. So without it, life can't happen. So it would have been necessary at the formation of the Earth. That's about as much as I can say on that.
Yeah, and again, this is we'll get someone from Alma or someone from one of the biologists to come on
Oh, yeah.
on board at some point. But the just this idea of having these more complicated versions of these chemicals being available and there early on is what you really want to sort of. It's a much more natural fit. It's funny, like now a lot of the thinking here on Earth is going into these ideas of the hydrothermal vents down at the bottom of the oceans as a potential
Right.
place where life got started. It's that classic, was it the Millikan experiment, where they had like a gas they had a beaker filled with those sort of primordial elements, ran some lightning through the bottle, and produced some of the more complicated elements that were, some of these building blocks, these amino acids. And now it looks like that same kind of chemical bath that's going on down at the bottom of the oceans, and the black smokers that are putting out this hydrogen rich gas is another potential way that you could have those things come together. And that's what makes it so exciting with, say, Europa and Enceladus, is that they've got a very similar environment. Clearly we're seeing this hydrogen gas leaking out of Enceladus, that again, more environments, more places. So
Exactly.
So let's move on to, oh, wow. So Larry Beckham just noted that it was the principal toxicant involved in the Bhopal disaster, which killed nearly 2,200 people initially and 87 people in total. I did not know.
Yeah, I was actually reading about that. It's really fascinating, just the opposites at work here, that this molecule can kill people, but it also creates life. So I don't know, just kind of interesting. So I appreciate you making that observation.
So let's move on to the other story that you've got this week, and that is that the WOW mystery signal from space finally explained.
Yeah, so this is pretty incredible. A lot of people have seen that famous image. It's a bunch of numbers, and a scientist has circled a column of them in red and just wrote wow in big letters with an exclamation point next to it. That was back in 1977, and the signal was detected by an astronomer using the Ohio State Big Ear radio telescope. And at that time, the radio signal detector was scanning the stars as part of the SETI project. So the astronomer captured a signal that was a little bit over a minute. It was a burst of radio waves, and he circled this reading, and he wrote wow next to it, hence the signal's name. And it was really unusual, and we have not been able to figure out the origin of this signal for about 40 years. And people have suggested all sorts of stuff. There are a lot of people who thought it could be an asteroid, it could be an exoplanet. People often outside the scientific community have instantly said, oh, it must be aliens. So just last year, a bunch of experts from the Center of Planetary Science gave a new suggestion. They said that the signal may actually have come from a hydrogen cloud accompanying a comet. And the idea behind this was that the frequency that the signal was transmitted at is the same frequency as hydrogen. And also the movement of the comet would explain why the signal wasn't seen again. So the team started doing a bunch of research, and they found that there were two comets that were in the sky that day that the signal was detected. And they looked at the radio signals from these comets, and one of them actually matched the WOW signal. And these particular comets were also surrounded by millions of kilometers of clouds of hydrogen. So it also supports the theory with the frequency. So this is a pretty big deal. If they're right, it solves this age-old mystery in astronomy. And they're acknowledging that this isn't an end-all be-all conclusion. There's actually a lot of skepticism as well from the OSU Radio Observatory where the signal was detected. One of the experts there says that the comets were too far away that day to have caused the signal. There's no prior evidence saying that comets can create that type of signal. But all the same, I think a lot of astronomers are pretty happy to have a potential answer. And then also, if it is the comets, this could help us kind of vet any other signals better.
Yeah, I mean, one of the things, I'm going to put the wow signal up here for a second, and I'm going to sort of explain to people a bit about how the wow signal works, just so you get some context. So I'm going to put this up now, so you can see the wow, and then you can see the 6EQUJ5, and then later on there's a 6 and there's a 7. So people are wondering, like, if you could just decode that 6EQ, like, what is the code there? But what it really is that it's the strength of the signal. So the telescope was pointed in this region of the sky, and all the ones are sort of normal background. It's like, think of it like just like a height of the signal. It's all just these ones and twos and fours, and so that's just background noise. But then the scale that they use to measure the strength of the signal goes 1 through 9, I think, and then just kept going through a bunch of letters if the signal strength was really, really strong. And so all this really does is it maps out to almost like a bell curve of strength of the signal. So there's not more information encoded in those letters. That's just a way to sort of, with one character, be able to show the strength of the signal during that duration. So if you're trying to sort of turn those numbers into like some secret alien code, it's not going to work. And as you said, that's exactly right, that astronomers were looking at different possibilities. I mean, one of the biggest ones is that it's actually terrestrial in origin, that it never came from space, that there's some kind of some kind of signal leaking onto their detectors here on Earth, and
Right.
and they've done follow-up observations looking in that exact same part of the sky, different telescopes, different wavelengths, again and again and again, and nobody has ever seen anything else come from that location ever again. It was this blip and it was gone. And so I think that comet idea is very interesting, be it that you've got something that passed through the field of view, provided that exact reflection of the, at that wavelength, and then was gone again and could never be seen again.
Exactly. And the fact that the signal came at the same frequency as the hydrogen as well, that really sold me on this theory. I thought that was pretty good evidence.
And this idea that the comet had not been seen before, like they hadn't discovered the comet, but maybe they had discovered
Right.
in that wavelength, right? And then
Exactly.
And then later on, they actually made the discoveries of those. And so I think the thing that's really fascinating is that those comets were again visible in the sky, and the astronomers were able to test their observations again.
Exactly. And they tested it 3 times, I think, because the comets appeared between November 2016 and then February 2017. So it gave them 3 opportunities. So it wasn't just a one and done kind of test. It was, had a few more examples.
And they replicated the wow signal.
Exactly. They
Right?
replicated it at the same frequency.
Yeah. So we know that those comets were passing through that area, but they hadn't been discovered in any other wavelength. And when those comets were observed again using a radio telescope, the same signal was seen. I mean, that
Exactly.
feels pretty compelling to me.
I know, to me,
Yeah.
I was really surprised when I started reading all of the people speaking out with doubt. I think that it's so important to do that in science, and to have those varying perspectives, and to have experts come out and say, well, we need more evidence before we can say this for sure. I think that that's really, really important. But at the same time, I think it's pretty compelling. But I'm also not a scientist.
Well, what's it like for you guys at Futurism to, like we always, I gotta know, like the universe today, we are always sort of walking that fine line. And some may think that we fall over the edge a little too often about sort of going down those kinds of rabbit holes and trying to sort of feed people's hunger and desire for, I'm not saying it's aliens, but it's aliens. And and so how do
Right.
you guys sort of walk that balance?
People are so, in many ways, and I'm the same way. I'd love to have a firm answer to everything. I feel that that's one of the reasons that so many people are compelled by science, and especially astronomy, anything about space in general, because as we learn more about our universe, you want those answers. But I think anyone in the field of science, or anyone who's looking for extraterrestrial life, is going to be continuously disappointed if everything you're wondering, is it going to be aliens? So I do agree that it's tough to walk that fine line, because you're so excited about stuff like this. Personally, I would obviously love if we could detect some sort of signal, but 9 times out of 10, maybe even more than that, it's not going to be extraterrestrial life.
9.9 million times out
That's
of
a little bit
10
more
million.
accurate, yeah.
But did you guys sort of deal with the whole Tabby star,
Oh, yes.
alien megastructure controversy,
Right.
or not even controversy, just mystery?
Right. No, I mean, that's fascinating in itself. I think that as humans, we look for answers to these things. And I can't remember the phrase that I want, but it's the most simple explanation is usually the most likely.
Occam's
So the
razor?
most simple,
Yeah.
exactly,
Yeah.
Occam's razor. So in this instance, the wow signal, when I heard that it was a comet, it was almost like a little bit of a letdown to me. It was like, that's not the most exciting answer, but it's still an answer, which is really exciting if that is indeed firm. So with Tabby Star, personally, I really highly doubt that it's any sort of like Kardashev scale level alien megastructure, Dyson sphere, cool stuff like that. Would love it if it was, but unfortunately, it's probably a more simple explanation.
But as a science communicator, though, like if you go too technical, and we said that earlier on with
Mm-hmm.
Universal by the
Yes.
book, that the math is poison. If you go too deep into the math, then people's eyes are gonna glaze over, and they're not, and just to have the negative result, the null result in the findings is less interesting to people than the intriguing possibility of the thing they've always hoped for. And when you guys are choosing stories over there at Futurism, how do you walk that line? Do you feel a sort of moral responsibility not to get overly hyped, but also to bring in the readers to learn more about the actual underlying science? How do you walk that balance?
Absolutely. Like, I think that it's so challenging at any media organization you have so many things as your priorities, especially in this day and age. Being an honest news source, you're constantly being scrutinized for that, for making sure you're not putting out, quote, fake news, or, you don't want to lose the trust of your readership. So it's vital to be able to be engaging while still, sharing accurate science, because even though it might not enthrall everyone, if the answer to something isn't super exciting, at least you're being ethical and you're being honest. So I think, like you keep saying, it really is a fine line, and it's something that's not easy to navigate. But at the end of the day, to us at least, it really all comes back down to being ethical and to sharing that knowledge. And even if it's not the most exciting knowledge, at least we're, putting out there for the people that might really want to learn about it.
Yeah. We get accused of being, overly clickbaity. Do you guys get that too?
It's so funny because it goes through cycles. The first one was, your headlines are so clickbaity. And then when people got bored with that, it was people yelling fake news at us. And you're always going to have those negative people, which I'm sure you've learned as well. And for every negative person, there's so many positive emails and comments and everything that we receive every day from readers, from teachers, from just people that are passionate about science, that makes the difference there. So luckily, you just kind of, push all those negative people to the back.
Yeah, yeah. For me, I find the most important thing as I go about like writing, doing the videos and writing articles on Universe Today and things like that, it's sort of like it's most important to be correct. And that is like the first like my first priority is to make sure that everything that I say is to the best of our understanding correct. Once I've sort of gone through that, then I want to make everything cool. And it's that, and that's the art, that's the fine line, because if we used to write articles on Universe Today and and no one would read them, right? It's like if a tree falls in the forest and and nobody hears it, then does anybody hear it? And so if we write an article that nobody wants to read, should we even bothered writing the story in the first place? And my answer now is no, right? Like literally, if we feel we can tell that a story is not going to be of interest to people, we'll let other people cover it. Like we're going to do the ones that we want to bring in the readers and are going to sort of engage our audience with the kind of stuff that we think is both factually correct and really interesting and cool, because we have we only have so much time in our day to follow this news.
Absolutely, I completely agree.
Yeah, and so it's more about like almost less, but more fascinating and interesting, and so they have to be scientifically correct and super interesting at the same time. That's our balance, and that's the lesson that we've had to learn. And and you only learn that lesson by kind of getting it wrong enough times. That's a tough lesson. I find that even for all of our journalists, for all of our journalists, for all of the people that work with me, we all have to make that mistake a bunch of times. You're like, oh, I got it wrong, right? I got overly enthusiastic. I didn't read the paper. I didn't understand what was going on. I followed the hype trail that everybody was going down. There was, as you can tell, we're killing time because it's just the two of us. There's only two stories. But there was a great story that came out from Dr. Jason Wright, who had joined us here on the Weekly Space Hangout about half a year ago. He's an exoplanet researcher, and he was one of the people who worked on Tabby Star, things like that. And he had just posted a thing about how to search for essentially extinct precursor civilizations in the solar system. You guys, I'm sure, had reported on it as well, about all of the places that we could go and look to find out if there are civilizations in the solar system before us, and what might the signs be. And watching his response to the way his story was handled was really interesting, because it was like everybody just went in the wrong direction, right? They're all like, Dr. Jason Wright is saying that there are aliens, that there were civilizations before us, and here's how we'll find them. And he was like, no. In fact, it's pretty obvious that there aren't any with all of the evidence that we've looked at so far. Here's a few more places that you might want to go look at, but that's all, And so I think that we, again, our responsibility is to get to that original intention from the researcher and make sure that that's preserved more than anything, that the underlying science. And then after that, we can kind of get crazy. There was a and the title is very, very, very important, but
Jolene is actually she's in the comments on the YouTube stream.
I can see her. Yeah, why is she over there, Jolene? You should be joining us in here, but I understand some people have to talk in text. But yeah, Jolene is over there in the comments
discussing
having the discussion.
And alien ethics.
Yeah. Yeah, and it's true. And Jolene is saying you can't make the title something that everyone will love. Far too many pedants and people who read too much into things saying a new paper does not mean that we that we did. And that's exactly right. That you're always going to have, if you push the line, someone's going to go, clickbait. You're clickbait. You're fake news clickbait.
Exactly.
Yeah.
Yeah. No, it's amazing. I don't think that people realize how much we agonize, and I'm sure your team does too, over titles, over making sure that they're accurate, that they're not misleading, that they're not going to upset anyone. Obviously, sometimes you want to create interest, but you don't want to offend anyone. It's an interesting line to walk.
Yeah. And it is like a never-ending source of a conversation. And so I do appreciate when the pedants slap me down, and I mostly appreciate there's a couple of fans who at the same time are very deeply scientifically knowledgeable and are able to sort of redirect me whenever I make when I am not precise and diligent about making sure that I've got the underlying science correct.
Absolutely. I've learned so much from readers who have sent in correction emails or just quick comments to give suggestions on how to make things clearer. Those constructive criticisms are always so helpful to me and to our team and stuff like that. So criticism can be absolutely fantastic at times.
So those were two stories that you worked on. Is there anything sort of not space related that you're working on, or is that your beat?
So I don't really have a beat. So I'm the managing editor at Futurism. So I just kind of do a little bit of everything. Space is totally my thing, though. I've always been interested in it. I went to a SpaceX launch a couple years ago.
Oh, really?
Yeah, it was fantastic. It was the CRS-9 resupply mission to the International Space Station. I got to go see OSIRIS-REx before it launched out in Colorado. So Space is just very interesting to me. A lot of what we've been covering at Futurism lately, though, has been climate change. Lots of great new renewable energy news, positive stuff like that. Also, I don't know if you're interested in cryptocurrency at all, but
absolutely,
that's been just blowing up lately. Ethereum,
Bitcoin, $2,800.
It's crazy. Everyone keeps talking about when the bubble is going to burst next.
Yeah.
So waiting on that to happen. But yeah, that's kind of what I'm interested in lately.
So where can people find out more about you and what you're working on?
So you can head over to futurism.com. You can find us there. We're on Facebook, we're on Twitter, Instagram, literally every social media, everything. If you guys are interested in following me at all, I'm on Facebook. I am on Twitter, is Saga of Sarah, Instagram, all that good stuff. But if you want to learn all about science, Futurism's the place to go.
Fantastic. Well, thank you, everybody, for joining us this week. I'm going to wrap it up a tiny little bit short. Big thanks once again, Jeff Forshaw, Universal, Guide to the Cosmos, and that other guy. Yes, that's it. Brian, if you want proper attribution, you got to come on the Weekly Space Hangout and show your face. That's what you got to do. Dr. Brian Cox, of course, that very super famous Manchester astronomer, cosmologist, particle physicist who mostly hangs out at CERN. Right. So if you haven't already, like this episode, why wouldn't you? Go ahead and subscribe to this channel. Again, why wouldn't you? There is an interesting collaboration happening shortly with me and Futurism. So they posted, I'm going to see if I can link this up here. They posted on there. All right. So what one thing do you most want to know about the universe? And now we've got 456 questions that I have to answer.
Go add more, guys.
Yeah, go ahead and add more. Yeah, go over to Futurism, go to their Facebook page, post any more questions. And so I'm going to answer, it'll be like one of my QA shows. I'm going to tackle as many as I can handle in the course of an hour or so. And that'll be appearing on their website at some point shortly. So, all right, let's go There we go. So once again, Astronomy Cast is going to be on in about 45 minutes. Thanks, as always, to the WSH crew. They're the people that provide this interesting chat down here. And really, they're the producers behind the show. They were the ones who got Dr. Jeff Forshaw here on the episode and help pick some of the stories that we tackle each week. So couldn't do this without them. If you want to join this amazing community, go to wshcrew.space and you'll be able to find out more. All right, we will see all of you next week and some of you in about 40 minutes. All right, see you later.